VCE Chemistry, Unit 4, Isomers. In this session, we'll talk about how isomers form into different structural and stereoisomers. And also, we will talk about how to identify chiral centers in an optical isomer, as well as how to distinguish between cis and trans isomers. So, first of all, isomers refer to molecules with the same number and type of atoms. So if it's an alkane, they have the same number of hydrogen and carbon atoms, but they are arranged in different ways. So the first category of isomers are called structural isomers. They include two subcategories. One is chain isomers that mostly refer to alkanes with different alkyl branches. Or it can be positional isomers. When we talk about positional isomer, we're referring to isomers with the same functional group, but that functional group can be attached to a different position. Then another category of isomers are a little bit different. They are called stereoisomers, and they are categorized into optical isomers, which mostly is two molecules who are the mirror images of each other, but they cannot be superimposed. And geometrical isomers, which is because of the restriction of a double bond of the rotation. So here is an example of chain isomers, that is the structural isomer. You can see that all three molecules have exactly the same molecular formula because they have the same number of carbon and hydrogen atoms. However, there are obviously three different molecules. These chain isomers can easily be identified if we try to name them using IUPAC naming system. A positional isomer is more straightforward. It's the molecule with the same functional group, but that functional group is on different carbons. So again, they're different molecules. We can also tell them apart by naming them. Optical isomers. When we talk about optical isomers, we talk about a chirality. So chiral objects. What are chiral objects? Chiral objects are the objects that, like your hands or your feet, right? Your left hand and your right hand, they are the mirror image of each other, but they cannot be superimposed onto one another. So like this, your left hand and right hand. If you want to put your right hand on top of your left hand, both palm facing down, then you'll notice that your thumb can never overlap with each other. And the little fingers also cannot overlap with each other. So our left hand and right hand are not the same. They are not the same kind of arrangement, spatial arrangement. They are chiral objects, and they cannot be superimposed onto one another. What does it mean, superimpose? It means basically what I said you do, right? You put the two things of the same orientation spatially if one can't fit exactly onto the other. Okay. So chiral objects normally lack a plane of symmetry. That's mostly why they are chiral objects. They are mirror images of each other. You feel like they're symmetrical somehow, but they're actually not symmetrical by themselves. Like your left hand and right hand, if you put them into a mirror, then they are actually sort of like symmetrical of each other, but one hand cannot be symmetrical. Like neither of your hand is actually symmetrical by themselves. But the opposite of that, which is achiral objects, they normally have a plane of symmetry. Okay. So it's hard to imagine how a chiral molecule looks like, but it's not hard to determine if a molecule is a chiral or not. That is, if an organic molecule has one carbon, any carbon, that is joined to four different groups in a tetrahedral arrangement, then that molecule will be a chiral molecule, because that carbon that's adjoined to four different groups, it will be the chiral center of that particular molecule. So a pair of chiral molecules like these two molecules. They're exactly the same. They have the same functional groups, the same the carbon atoms, number of carbon atoms, same number of hydrogen atoms and nitrogen atoms, but they cannot be superimposed, just like our left hand and right hand. So they are a pair of enantiomers of each other. So when we talk about enantiomer, we don't say, oh, this is one enantiomer. We often say they are enantiomers of each other. It has to come in pairs. So an example of a chiral and achiral molecule. So for example, look at this carbon at the bottom here. It has two groups are the same, like both of them are fluorine connected to the same carbon, right? So that carbon can easily be superimposed onto each other. You can put a mirror, and the mirror image of that is B, but B, if you rotate A a little bit, it can look exactly like B, right? However, look at this carbon on the top here. There are 4 different groups on this carbon. If we draw the mirror image of this carbon atom, it will look like this. And the mirror image can never superimpose onto the original molecule. So these two are a pair of enantiomers. So in VCE chemistry, all we ask to do is to identify the chiral center in the molecule. So remember, the trick is to find the one carbon that's connected to 4 different groups. And when we look at different groups, we have to look at the entire group that's connected to one carbon. So for example here, our chiral center is this one. Because this carbon is connected to 4 different groups. And you'd be like, wait a minute, isn't this carbon connected to 2 of the CH2 groups? Well, you have to look at the entire group that's connected to that particular carbon. So everything that's on the left, compared to everything that's on the right, and compared to everything that's on top and at the bottom. Okay? So if a carbon is CH2 group, so all CH2 or CH3 groups can be straight away eliminated because they obviously have the same atoms connected to it, so they won't be the chiral center. The chiral center can only be the carbon atom that is connected to all 4 different groups. Okay. In that similar logic, a carbon that are involved in double bond or triple bond cannot be the chiral center because obviously they are sort of like symmetrical to some extent. So that carbon is our chiral carbon. You can have a try, look at this molecule, which carbon is connected to 4 different groups. It's that one, right? And in this molecule, obviously it's that one. Okay, so CH3 groups will never be, and if a carbon is in a ring, it's not going to be a chiral carbon, and this carbon has a double bond, it's not going to be a chiral carbon. It has to be 4 different groups. Okay. Geometric isomers, we are referring to cis and trans isomers. So it's normally due to the restricted rotation of a carbon-carbon double bond, resulting if there are 2 different groups connected to the same carbon, and it's the same case for both carbons, then you will have a cis and trans isomer. That is, if 2 of the larger group are on the same side, they're called the cis isomer. And if 2 of the larger groups are formed on different carbons, then they are the trans isomer. So example here, look at these 2 different alkenes. If we try to name them, they'd all be but-2-ene. But these 2 are actually 2 different molecules. They cannot be superimposed onto each other either. Okay, so this molecule, you have 2 of the larger groups on each side. So compare hydrogen and alkyl group. Alkyl group is larger. And then you compare this one, also alkyl group is larger. 2 larger groups of each carbon are on the same side. That's a cis isomer. And the opposite of that, if you are on 2 different sides, then it's a trans isomer.